Okay, let's unpack this. Have you ever wondered how your phone figures out what song is playing just from a little snippet?
Or how doctors get those incredibly detailed 3D images of your insides without, any surgery.
Exactly. Well, deep down, often at the heart of that tech, there's some honestly really fascinating math. Today, we're doing a deep dive into the discrete Fourier transform, DFT. It sounds maybe a bit intimidating.
It can, yeah.
But it's incredibly powerful and, frankly, kind of fun once you get what it's doing.
And we'll also look at its close cousin, the Laplace transform.
Right. And show how these mathematical tools, these shortcuts, really give us this amazing way to see hidden patterns in data, in signals.
Precisely. So our mission today is, well, to cut through that complexity. We've got a stack of sources here. Wikipedia deep dives on DFT and Laplace, technical tutorials, engineering applications.
All the good stuff.
Yeah, the works. And we're going to pull out the really important bits. Help you understand not just what they are, but, crucially, why they matter. How they impact tech all around us.
Get ready for some aha moments, hopefully.
Let's hope so.
So let's kick off with the discrete Fourier transform, the DFT. Maybe start with something relatable, like a sound wave.
Good idea. So imagine sound, it's this continuous wave, pressure changing over time.
Right.
But your phone, or any digital device, it can't capture everything continuously. It takes tiny snapshots, samples, at really regular, quick intervals.
Giving us a sequence of numbers, basically. Data points.
Exactly. A finite sequence of equally spaced samples. And that's what the DFT works on.
Okay, so what does it do with those samples?
It transforms them. It converts that sequence of time-based samples into a different sequence, same length, but this one represents the frequency content. It's the frequency domain representation.
So like breaking down music into individual notes.
That's a great way to think about it, yeah. It tells you which frequencies are present in that original signal and how strong they are, their amplitude and phase. It's like a digital alchemist turning time into frequency.
A digital alchemist, I like that.
Yeah.
So where does this alchemy show up? Everyday applications.
Oh, everywhere. Digital signal processing, DSP, is the huge one. Analyzing anything that changes over time.
Sound waves, radio signals.
Daily temperatures, stock prices, anything sampled over time. Noise-canceling headphones rely on this stuff. Voice recognition, music streaming.
Wow, okay.
Then there's image processing. The samples can be pixel values along a line in an image. So sharpening photos, finding patterns, medical imaging.
Right, you mentioned the 3D scans earlier.
And it's also used, maybe less obviously, as a computational tool for solving certain complex math problems like partial differential equations.
Okay.
And even for speeding up basic operations like convolution, which is common in signal processing, or even multiplying really, really big numbers.
Big numbers, like cryptography.
Exactly, like in cryptography.
Now, people often mention FFT when they talk about DFT. Fast Fourier transform. Are they different things?
Good question. They're very closely related, but not quite the same. The FFT isn't a different transform. It's an incredibly efficient algorithm to calculate the DFT.
So DFT is the what? FFT is the how, a fast how.
Perfectly put, yes.
Yeah.
Because the FFT is so much faster, especially for large amounts of data, it's almost always the way the DFT is actually computed in practice.
Which is why people kind of use the terms interchangeably sometimes.
Exactly. In practice, if someone says they're using an FFT, they are fundamentally calculating a DFT.
Okay. So delving just a little deeper, without getting lost in formulas, the DFT takes n input numbers, transforms them into n output numbers. You mentioned these involve amplitude and phase.
Right. The inputs and outputs are generally complex numbers, which sounds scary, but just think of them as numbers that hold two pieces of information: magnitude, or strength, and phase, which is like timing or position in the cycle.
So it captures more than just how much frequency there is.
Precisely. It captures its relationship in time as well. And crucially, there's an inverse DFT. You can take those frequency components and perfectly reconstruct the original time signal. It's a two-way street.
So beyond just this conversion, what makes the DFT such a workhorse? You mentioned properties, like mathematical superpowers.
Definitely. These properties are why it's so useful. One fundamental one is linearity. It's predictable. If you add two signals together, their DFTs just add up. If you scale a signal, its DFT scales the same way.
Makes sense. Easy to work with.
Very. Then there's stuff like time and frequency reversal. If you flip the input signal backward in time, the frequency output also flips. There's this nice symmetry.
Yeah.
And it's periodic. The output sequence repeats every n samples. You only need to look at the first n values.
What about the shift theorem? I hear that mentioned.
Yeah, that's important. If you shift your signal in time, like delay it slightly, it doesn't scramble the frequencies. It just changes their phases in a very predictable way.
Yeah.
It multiplies the DFT by what's called a linear phase.
Okay, predictable changes.
And the flip side is true, too. If you modulate the input signal, change its phase in time, it shifts the whole frequency spectrum.
Now, you mentioned convolution earlier, and this circular convolution theorem. You said it was a big deal.
Oh, it's huge. Probably one of the most important properties computationally. Convolution, think of it like applying a filter or an effect, like reverb in audio. Mathematically, it's quite involved.
Okay.
What the theorem says is, doing that convolution in the time domain is exactly equivalent to just doing simple multiplication in the frequency domain.
Wait, so you transform both signals with DFT?
Right. You transform the signal, you transform the filter or the effect.
Then just multiply the corresponding frequency numbers together.
Exactly. Element by element multiplication,
Right.
which is way faster computationally than doing the full convolution. Then you do an inverse DFT on the result to get back to the time domain.
Wow.
That
That sounds like a massive shortcut.
It is. It's the reason FFT-based convolution is used everywhere. The circular part just means the math treats the signal as if it wraps around, like the end connects back to the beginning. That's a detail needed for the math to work perfectly.
And this property is unique to the DFT.
Fundamentally, yes. The DFT is basically the linear transform that turns this circular convolution into simple pointwise multiplication.
Neat. Any other key properties we should touch on?
Well, there's the fact it can be viewed as a matrix operation, and if you normalize it right, it becomes a unitary transform.
Unitary meaning?
Meaning it preserves energy or lengths of vectors, like a rotation in space. It doesn't stretch or squash the data, it just represents it differently. Also, its eigenvalues are surprisingly simple. Just +1, -1, plus I, or I. Doing the DFT 4 times gets you back exactly where you started.
4 times? Like cycling through representations.
Exactly. And finally, there's the uncertainty principle, similar to Heisenberg's in physics.
You can't know position and momentum precisely at the same time?
Right. For the DFT, it means a signal cannot be simultaneously sparse, meaning having very few non-zero or significant values in both the time domain and the frequency domain.
So a trade-off. If it's very simple in time,
It must be spread out and complex in frequency.
and if it's made of only a few pure frequencies.
Then its representation in time has to be complicated, spread out over time. You can't have maximum simplicity in both domains at once.
That sounds really relevant for data compression.
Hugely relevant. It's a fundamental limit and also something we exploit.
Okay, that's quite a list of properties. Let's bring this back to the real world. How do these actually translate into impact for you, listening?
Right. Let's ground it. Spectral analysis is the most direct work, analyzing frequency content.
Like we said, seeing the notes in music.
Exactly. You record audio, plot it over time, it might look like a jumble. You apply the DFT, plot the magnitude of the result, and boom, peaks show up.
The dominant frequencies.
The dominant frequencies, the fundamental pitch of a voice, the harmonics, maybe some noise frequencies. It's like an X-ray for sound structure.
Are there things that can go wrong? Distortions.
Oh, yes. Good point. We mentioned sampling earlier. If you don't sample fast enough below the Nyquist rate, high frequencies can get disguised as lower ones. That's aliasing.
Like a wagon wheel effect in old movies?
Precisely. That's visual aliasing. Same principle. The other issue is leakage. Because we always analyze a finite chunk of signal, not an infinite one, frequencies can seem to bleed into their neighbors in the DFT output.
Making the peaks look wider or less distinct?
Exactly. We use techniques called windowing, basically shaping the edges of our data chunks smoothly to minimize this leakage.
And what about zero padding? I've heard that term with FFTs.
Zero padding. That's adding a bunch of zeros to the end of your time domain data before you do the DFT or FFT.
Does that add new information?
No, it doesn't add any new information about the original signal. But what it does do is give you more points in your DFT output. It effectively increases the resolution of the frequency plot.
So the graph looks smoother, easier to see the peaks.
Exactly. It interpolates between the frequency points you would have gotten otherwise, making the spectrum look denser and often easier to interpret visually. Let's try that quick example. Say we have a tiny audio signal, 4 samples. Let's say the values are x, 1, 1.5, -0.5, and -1.
Okay, just 4 numbers.
We run the DFT. We get 4 complex numbers out, maybe something like x equals 0, 1.5, 1.5j, 1, 1.5 plus 1.5j. Don't worry about the calculation.
Okay.
The key is we then look at the magnitude of these complex numbers. How big are they? We'd get something like x is 0, 2.11, 2.12 roughly.
So 0 at the start, then peaks.
Right. Plotting those magnitudes against frequency indices gives us the magnitude spectrum. The peaks at indices 1 and 3, around 2.12, tell us those frequencies are the most prominent components in that tiny original signal snippet. Index 2 has some energy, index 0 has none.
That really clarifies how it reveals the hidden frequency structure. Very cool. What else uses this X-ray vision?
Well, optics and diffraction. It's used to model how light waves or even electron beams spread out and interfere. Thinking in terms of spatial frequencies.
Spatial frequencies.
Yeah.
Like patterns in space instead of time.
Exactly. And this directly leads to tomography, like medical imaging, CT scans, MRIs. They fundamentally rely on measuring projections through an object and then using algorithms related to the Fourier transform, specifically something called the Fourier slice theorem, to reconstruct the 3D internal structure.
Wow. So DFT concepts are literally letting us see inside things.
Absolutely. And data compression. Many common methods, like JPEG for images or MP3AC for audio, use transforms related to the DFT, often the DCT, discrete cosine transform, which is a close cousin.
How did that work?
They transform chunks of data into the frequency domain. Then they notice that often a lot of the energy is in the lower frequencies. The high frequency components often represent fine details or noise that our eyes or ears aren't as sensitive to.
So they just throw away the high frequency information.
Well, they quantize it more coarsely or sometimes discard it entirely, especially the very high frequencies, because those components often take up data but contribute less to the perceived quality. Then they store the remaining frequency info efficiently. That's how you get much smaller files.
Clever. Exploiting that frequency representation.
Exactly. And we touched on solving partial differential equations, PDEs. These equations describe physical phenomena, fluid flow, heat, waves. They're often really hard to solve directly.
Calculus nightmares sometimes.
Can be. But applying the DFT, or its continuous counterpart, can turn differentiation and integration into simple multiplication or division in the frequency domain. So the PDE becomes a much simpler algebraic equation.
Solve the easy algebraic ones.
Solve that in the frequency domain, then use the inverse DFT to transform the solution back to the original space or time domain. This is the core idea behind spectral methods, which are super powerful in scientific computing.
Okay, one more application. You mentioned polynomial multiplication. How does DFT help multiply numbers?
It's a fascinating application, especially for really big numbers, like hundreds or thousands of digits long, which you see in cryptography.
Right.
You can represent a huge number as the coefficients of a polynomial. So multiplying 2 huge numbers is like multiplying 2 high-degree polynomials.
Which is normally quite slow, right? Lots
Right.
of cross multiplication.
Very slow, yeah. It scales badly. But polynomial multiplication is mathematically equivalent to convolution of their coefficient sequences.
And convolution in the time domain.
Is multiplication in the frequency domain. So you take the coefficient sequences, DFT them, using an FFT, of course, do the fast element-wise multiplication in the frequency domain, and then inverse DFT the result.
And that gives you the coefficients of the resulting polynomial, which represents the huge product number.
Exactly. It turns a very slow operation into a much, much faster one thanks to the FFT algorithm. It's a cornerstone of fast arithmetic for large numbers.
Okay, the DFT is clearly amazing for these discrete sample signals. But you mentioned continuous signals earlier, like actual sound waves or electrical currents. That's where the Laplace transform comes in.
That's exactly its domain. The Laplace transform, named after Pierre-Simon Laplace, is designed for continuous functions of a real variable, usually time.
This is not samples, but the actual smooth function.
Right. It's an integral transform. It takes that time domain function of ft and converts it into a function of a complex variable, usually called s. We call this the complex frequency domain, or the Hasse plane.
Complex again. So S isn't just frequency.
No, and that's key. S is written as plus IO. The Hasse part is angular frequency, like in the Fourier world. But the sus, the real part, represents exponential decay or growth.
So it can handle signals that aren't just oscillating forever, but might be dying out or even increasing.
Precisely. That's one of its major strengths over the basic Fourier transform. It can handle a wider class of functions, including unstable or transient ones.
And what's its main superpower? Like the DFT's convolution theorem.
Its main superpower is turning calculus into algebra. Specifically, operations like differentiation and integration in the time domain become simple multiplication and division by S in the Laplace domain.
So it makes solving differential equations much easier.
Dramatically easier, especially linear ordinary differential equations with constant coefficients. They become algebraic equations in CRES, which you can often solve with basic algebra. Then, just like the DFT, there's an inverse Laplace transform to get your solution back into the time domain.
Makes sense. So where is it indispensable? Engineering.
Oh, absolutely fundamental in electrical engineering, control theory, mechanical systems. Anywhere you're analyzing dynamic systems described by differential equations.
Like designing controllers for robots or aircraft.
Exactly. Analyzing stability is a huge application. Will the system behave predictably, or will it oscillate out of control? The Laplace transform helps answer that. A key concept here is the region of convergence, or ROC.
ROC, what's that about?
It's the set of values for which the Laplace transform integral actually exists, where it converges. It's not just a mathematical footnote. For engineers, the ROC tells you critical things about the system, like whether it's causal, doesn't respond before an input, and whether it's stable.
So the location of things in this plane matters.
Very much so. For example, for a system to be stable, the poles of its Laplace transform, basically values of S where the function blows up, must all lie in the left half of the complex plane, where the real part is negative.
Negative sigma, meaning decay, not growth.
Exactly. It corresponds to decaying responses, which means stability.
And does it share properties like linearity with the DFT?
Yes, it's linear. Combining signals in time combines their transforms linearly. And as we said, differentiation in time becomes multiplication by S, with some terms for initial conditions. Integration in time becomes division by S.
And convolution?
Same magic trick. The convolution theorem holds here too. Convolution of two functions in the time domain becomes simple multiplication of their respective Laplace transforms in the S domain. Again, a massive simplification for system analysis.
Okay, so they both transform signals, turn convolution into multiplication. They sound really similar in purpose. How related are the DFT and the Laplace transform? Are they like siblings, distant cousins?
Definitely in the same family. You could say the Fourier transform, which the DFT is the discrete version of, is like a special case, maybe a very important sibling, of the more general Laplace transform.
A special case? How so?
Remember, isn't the Laplace transform is complex, S plus I?
Right, with the decay growth part and the frequency part.
If you specifically set that real part, SUD, to 0, so you're only considering SIO, purely imaginary values.
Just the frequency axis and that's point.
Exactly. Then the Laplace transform essentially becomes the Fourier transform, the continuous version.
Ah, okay. So the Fourier transform is just looking at pure, steady oscillations without considering growth or decay.
That's a great way to put it. The Laplace transform, by including that term, can handle functions that grow or decay exponentially, functions that the standard Fourier transform might struggle with because their integrals wouldn't converge.
So the Laplace transform is more general because of that damping factor. It helps make sure the math works even for signals that aren't perfectly contained.
Precisely. That exponential factor ETH in the Laplace integral helps tame functions that might otherwise go off to infinity. It's more robust for analyzing things like system transients, stability, or signals that have distinct start and end behaviors.
Is there a connection to discrete signals too? Like bridging DFT and Laplace?
There is. There's something called the Z transform, which is kind of the discrete time equivalent of the Laplace transform. The Z transform is essentially the Laplace transform of an ideally sampled continuous signal. If you make a specific substitution relating Z to S, it shows how these continuous and discrete domain tools are all deeply interconnected.
So maybe Fourier DFT is best for analyzing the frequency content of stable, ongoing signals.
Right, like analyzing a steady musical tone or a stable radio wave.
While Laplace is better for analyzing the overall behavior of systems, including how they start up, settle down, or even if they become unstable.
You've got it. Laplace handles the transience and stability questions more naturally because of that complex frequencies. Fourier excels at pure frequency decomposition of well-behaved signals. They're complementary.
Wow. This deep dive has really peeled back the curtain, hasn't it? These mathematical ideas, DFT, Laplace, they seem abstract, but they're genuinely the unsung heroes behind so much modern tech.
They really are. From analyzing music, like you said, to designing incredibly complex control systems for aircraft or power grids, These transforms are indispensable tools.
They let us break down complexity, see the underlying structure.
Exactly. Decompose signals into simpler building blocks, understand dynamics. So the next time you see a sharp MRI image or have a clear video call or just, use almost any digital device, maybe give a little nod to the silent, powerful work of the discrete Fourier transform and the Laplace transform doing their magic in the background. What part of this stands out most to you, thinking about how these shortcuts change our digital world?
That's a good question to ponder. We certainly hope this deep dive has given you, our listener, a new appreciation for this hidden math that, well, makes our world tick.
Hope so.
Until next time, keep exploring, keep questioning, and keep deep diving with us. And here's something to think about. How might this ability, this instant switch between seeing a signal over time and seeing its frequency components? How might that lead to breakthroughs we can't even imagine yet? What new ways of analyzing or manipulating information does that unlock?